mention that we have Women in Circuits Bay Area Chapter Chair Yildiz joining us this year as Vice Chair, joining the committee. So we'd like to thank her, and also Ali, our past advisor and Vice Chair, is going to help us as the chair of the chapter as I'm stepping down this year. Just a couple of logistics as always for the cell phones and the questions. Unless the speaker would like to keep it interactive, just please keep it to the end of the talk. With that, I'd like to ask Ali to do the intro. Thank you very much.
Thanks, Sharif. We are really, again, let me welcome you as well. We are lucky today that we have a great speaker, Professor Sophia Shao, who has recently joined the University of California at Berkeley, is going to give a talk today regarding scalability of the machine learning accelerators, and in general, some methodology and compilers that how can you really put these things together and make them very efficient. So basically a platform for the hardware and how you optimize the hardware. We are really lucky to have this talk. Professor Shao, before joining Berkeley, she was a senior research scientist at NVIDIA. So the work has got a lot of industrial relevance. And in fact, she's going to give you guys some perspective of some research, recent papers at VLSI, at Hot Chips. So I personally I'm excited to listen to this talk. Professor Shao has received her PhD from Harvard University. And of course, her field of research is computer architecture. And I think that she's heavily focusing on these data flow architectures and these domain-specific architectures for accelerators that we will hear from. One of the things I want to point, she's got all kinds of awards and best thesis awards and all kinds of things. I want to mention one of them, that she's got this micro best paper award, and that's pretty big deal in the architectural world. So let's all not waste any more time and give the floor to Sophia. Thank you very much for being here.
Okay, well, thank you everyone for coming, especially with today's weather. It's really good to see you all here. And thank you, Ali, for the really nice introduction. So as Ali mentioned, I'm Sophia Shao. I'm a new faculty at UC Berkeley. And before I joined, I was at NVIDIA for a few years and working on accelerators, especially in the deep learning space. So in today's talk, I'm going to talk about some of my past work in the domain-specific accelerator space with a focus on thinking about scalability and productivity for deep learning accelerator design. I will also briefly talk about some of our ongoing work at Berkeley in further optimizing this space. So let's get started. So it's a really exciting time to be in the computing industry. We're observing an increasing demand for computing power, ranging from mobile processors to all the different kinds of Internet of Things and all the way to data centers. What's really exciting is that with the increasing number of devices and sensors, all the different kinds of data coming in, we also need a lot of compute power to process those data as fast as possible. Well, unfortunately, probably many of you are already pretty familiar with this, Moore's law won't help us in this process. After driving the semiconductor industry for more than 5 decades, Moore's law may finally start to slow down. So if you look at the plot showing here, which plots a historical Intel's historical technology scaling trend in the past decade. In the past decade, at the very beginning, Intel has been following this Moore's law quite closely by introducing a new generation of technology every other year. However, if you look at more recent technology, we definitely see things are slowing down. And not only the size of the transistors are not getting much smaller, the transistors are also not getting much better. We're not getting much better power, not getting much better performance, but the cost of the transistors, especially in the advanced technologies, become a lot more expensive. So with the increasing demand of computing power and the slowdown of technology scaling, we are really in the best and the worst time of our computing industry. So what can we do as the practitioners in this community to help the society actually to address the computational challenge? Well, one promising solution is the use of domain-specific accelerators. So what are they? They are basically customized hardware that are designed for an application or a domain of application. A really good example of domain-specific accelerators is in Apple's SoC. So this is what in Apple's 10S processor that was released a couple of years ago. It's really interesting. What's really interesting is that if you look for CPUs or GPUs in this die photo, they are actually pretty small. They only take roughly 15% of the entire die area. What's really interesting is that more than half of the die area is spent for non-CPU nor GPU blocks, many of which are domain-specific accelerators. A good example of domain-specific accelerator is this neural engine here, which are basically customized hardware that's designed for deep learning to make sure those applications can run very smoothly. Over the past decade, we have been also observing a new increasing trend of the number of specialized IP blocks across generations of Apple's SoC. So the natural evolution of this trend is a growing volume and also diversity of different specialized accelerators in our future products for better efficiency and performance. So while domain-specific accelerators give us a lot of efficiency and performance improvement, it also poses a unique accelerator design effort challenge. What do I mean by that? Well, here is another die photo from NVIDIA Xavier SoC. Very similar to Apple's SoC, it also have a range of different processing units. They have CPUs, GPUs, and all the different accelerators for deep learning, multimedia, computer vision, or image processing. One thing really interesting is that during the announcement of this Xavier processor, it highlighted as one of the most complex SoC that we have ever made. It costs roughly 8,000 engineering years to build this processor. So to put this number into context, right, the entire NVIDIA workforce is roughly 10,000 engineers. And then if you factor in the Bay Area salary into this 8,000 engineering hours, well, just the labor cost is pretty significant. So as an industry, what we really need to think about is why spend so much time in designing today's modern processor, and how can we improve that? So here is a rough diagram of two different features that were factored in our NVIDIA system in the past couple of years. So those two features are both accelerators, but of different complexity. Feature one is a bit more complex, requires system integrations, while feature two is more a standalone accelerator. So what we noticed that typically, if you think about project life cycle, it takes roughly 3 to 5 years from the initial inception of idea to the final productization. Over this cycle, two components take the most design time. One is architect, where we think about, we're trying to understand applications behavior, think about different mechanisms to make it run faster. And then we get to the implementation stage, where we implement the design for our target platform. And more importantly, we need to verify that to make sure they actually match our original spec. So moving forward, if we think about the increasing number of accelerators that we need to build, the unique feature or the number of unique features in our future generations of hardware is not limited by power, it's not limited by area, but will be limited by design effort. Specifically, if you think about the design complexities challenge that we mentioned earlier, to make sure that we can deliver all the different accelerators, we need to think really hard what we can do to systematically lower the hardware and software design cost and to make it realizable for all the different hardware that we're planning to build. Specifically, we need to think about accelerator generation. How can we produce all the different hardware? And accelerator integration. How can we integrate them together as the entire system and work together for domain or multiple domains of applications? Finally, one area that has been typically overlooked is programmability. How can we make sure those accelerators is actually accessible for high-level programmers and can be fully integrated into their application development pipeline? With that, my research vision is to automate the design process of accelerators. My work has spanned the entire stack of the design process, from application characterization, help designers to understand the different application behaviors, to building fast and accurate architecture simulators to help the designers easily navigate the power, performance, and area design space to produce an efficient accelerator design. More recently, we have been focusing on accelerator design in the machine learning domain, where we have been exploring different mechanisms for data movement, tiling strategies, and also sparsities, and more recently, the scalability paper that Ali mentioned earlier. And then on the productivity side, we are also interested in what we can do in the design flow to actually make it easier for our accelerators to be designed and also verified. More specifically, we have been experimenting different high-level synthesis methodologies to make sure that we can speed up the design process. Finally, we are also very interested in hardware prototype. That's actually a way to actually validate our ideas and see what we were missing in the design process. So over the past years, we have been also building different hardware prototypes, especially in the machine learning space, to actually test our ideas and also help us to reflect what more we can improve in the design process. So in today's talk, I'll be focusing on two of my past work. The first one is on the scalability of machine learning accelerators. That'll be our Simba work at Micro, that published at Micro this year. I will also talk about, from the design methodology side, what we can do to systematically evaluate the design space using a generator-based approach that was also published at Hot Chips and ICCAP this year. So, well, let's first start with the Simba approach. So actually, before I move on, it's really good to have a lively discussion. So if you have any questions, feel free to just let me know, and we can start the discussion during the talk. So first, let's think about scalability. So when we think about accelerator, especially deep learning inference accelerator, what is the first thing that comes to your mind? Is that a tiny little mobile device that speeds up inference in your mobile phone? Or is that a medium scale accelerator, for example, for self-driving cars, that to make sure that your application can run not only efficiently, but also accurately? Or is that a beefy data center scale accelerator for all the different deep learning inference that exists in our data center? Well, the truth is, all of these are deep learning inference accelerators. So different from training, inference is needed across a wide range of markets. However, it is infeasible to build a unique hardware for each of the individual markets due to the high design cost in the design process. At the same time, inference is also intrinsically scalable with abundant parallelism. Together with recent advances in multi-chip module-based package-level integration, there are actually possibilities to build a scalable system for different markets with only one chip tape-out. What do I mean by that? This is what we call the multi-chip module-based approach. This idea has been around for a while, right? So if you think about what are the advantages of multi-chip module-based approach. First, it enables us to build systems that are larger than the radical limit, which has already become a concern in today's CPU or GPU market. How can we build bigger systems? Well, second, if you think from design cost point of view, smaller systems are also cheaper to design and also provide better yield. And finally, from the time to market, as we mentioned earlier, for an application for demand that across so many different domains, we really need to want to make sure that we can provide or support all those markets simultaneously. So let's say in the case of deep learning accelerator, instead of designing and fabricating different products for different design markets, with a multi-chip module-based approach, we can actually do one chip tape-out, and then maybe a one chiplet system for the mobile market, 4 chiplet system for the self-driving car market, and a 36 chiplet system for the data center market. Well, of course, this kind of benefit does not come for free, right? If you think about what are the potential problems with this multi-chip module-based approach, from architecture point of view, the area, energy, and latency of the chip-to-chip interconnect or chip-to-chip communication will play a bigger role in future scalable system, especially large-scale system, in the way we think about scalability and the productivity. So with that, today I'm going to talk about our paper, Simba, which is the first multi-chip module-based deep learning inference accelerator that we designed, implemented, and fabricated 2 years ago. So in today's talk, I'll briefly first talk about the Simba test chip and focusing on the package, chiplet, and the processing element architecture. I will also talk about some of the characterization that we did with our prototype and highlighting the implications of the non-uniform latency and the bandwidth that coming from the network package in our system. Finally, I will talk about some of the optimization that we can do in terms of mapping computation to our hardware and some of our measured results on that front as well. So let's start from the Simba test chip. So as I mentioned earlier, this is a multi-chip module-based architecture for deep learning inference. The picture in the middle is what our package looks like. Each of the Simba package have an array of 6 by 6 Simba triplets. And if you zoom in to each Simba triplet, and then you get the die photo on the right. So inside a Simba triplet, we also have an array of processing element, global processing element, and the RISC-V core as a controller in our system. With the chip-to-chip interconnect was used, we are using the ground reference signaling technology for our chip-to-chip interconnect, which is also a technology that has been developing in the NVIDIA circuit research group. If you look at the overall spec of our system, we are able to achieve 128 tera operations per second while only consuming roughly 0.1 picojoules per op. That translates to roughly 10 TOPS per watt for a large system like this. And the math we're doing is 8-bit integer in this case. So for this Simba architecture in today's talk, I'd like to highlight 2 aspects. The first part is the non-uniform communication. What do I mean by that? If you think about large-scale system, especially with package-level interconnect, it's really challenging to have one uniform network to connect all the different components together. So to address the communication limitation, we use a non-uniform or hierarchical network approach, where we have both a network on chip that are used to connect all the different processing elements together, and the network on package that are used to connect all the different chiplets together. So if you look at our network on chip design, we have a 4x5 mesh topology to connect 16 PEs, 1 global PE and 1 RISC-V processor together. We also use cut-through routing with multicast support to actually support a large amount of communication that actually exists in the deep learning application. On the network on package front, we also use the 6x6 mesh topology for simplicity and also manufacturability. That was used to connect 36 chiplets together in our package. And in each of our chiplets, we have a NOP router or network on package router that is actually used to communicate, to connect both our network on chip and also network on package together. We also use a configurable routing to avoid any bad links or bad chiplets that may actually appear in the manufacturing process. If you think about the latency and the bandwidth of our NOP, it delivers roughly 20 nanoseconds per hop and with 100 gigabytes per second per chiplet. So here we talk about the communication interconnect architecture. Let's take a look at what are different processing elements being connected together. So here we also use a fully distributed processing element architecture, where we have a fully distributed weight buffer that are used to store the weights in the processing elements, and a small input buffer that is used to temporarily store the input activation in the processing. The core of the computation is actually performed in an array of vector MAC units that takes weights and also input activation, and then do the multiply and accumulate and produce the partial sum that are being accumulated in our accumulation buffer. Each processing element also have a router, and the lines become very zigzagged. But the router is supposed to populate the data to our wait and input buffer that I mentioned earlier. It can also be used to actually communicate to partial sum accumulation, where we take the partial sum from the previous PE, do accumulation locally, and then send the partial sum out to the next PE. For some of the cases, if this PE is actually doing the final calculation, we can also support fused computation, where we can do truncation, ReLU, pooling, and also scaling, and bias addition in the post-processing unit before we send the data out to other PE or global buffer. So if you think about this kind of large-scale computational substrate, right, one big challenge is actually how you map the computation to all the different processing elements, both on chip and also on package. So here I'm going to briefly talk about our baseline tiling strategy or mapping strategy here in our system. So in this example, I use blue tensor to represent input activation, green tensor to represent weight in the computation, and the red tensor to represent the output activation. And then in the example system with 4 chiplets, we can take a model parallelism approach where we partition our weight tensor along the input channel and also output channel dimension, and each unique chunk is being assigned to each chiplet. So with that, with our 4 chiplet system, each of them has a unique copy of different portion of the weight tensor. And then to perform convolution, we actually send the input activation or multicast input activation across different chiplets so that they can perform convolution, and then also support partial sum reduction across triplets for the output activation. And then if you zoom in to each triplet, we can further break down the weight tensor across our array of processing elements, and then do input activation multipass across PEs, and also partial sum reductions across PEs to produce the final output activation. So in this simple cartoon, I only show like row-wise multicast and column-wise reduction, right? But our communication substrate is very flexible that can support multicast and also reduction along any arbitrary dimensions. That was actually very important to find the efficient mapping in the final evaluation bring-up process. And this example also focuses on model parallelism, but we also support data parallelism in the system. So I talk about the 2 features of architecture, the non-uniform network and also the PE architecture design, and how we map computation to our system. Next, I'm going to talk about some of the characterization we did with our test chip, with some of the highlights of performance and energy efficiency, and some of the challenges that we observed. So here is our measurement setup. So if you look at the red rectangle in the middle, that's basically where our package is, with a huge cooling substrate there. So in our paper, we characterize different networks of performance on our system. In today's talk, I'll be mostly focusing on the ResNet in today's presentation. So first, we compare our Simba package with GPUs for both performance or throughput on the left and energy efficiency on the right. So here we selected 2 GPUs. One is the V100, which is one of the most powerful GPU these days, and also T4, which is a GPU that's tailored for data center inference. So when we run ResNet with low batch size on Simba, our throughput is almost like 2x better throughput compared to V100 and T4. And we look at energy efficiency, we can achieve up to more than 3x better energy efficiency compared to V100, and 2.6 or 7 better energy efficiency compared to V1. T4, actually. One thing you may notice that we stopped at batch size 2. The reason for that is that our system is a test chip, so we didn't really put a DRAM controller there. So we basically stop our measurement whenever our on-chip SRAM is not able to hold all the data, because then it will eventually be bottlenecked by our DRAM bandwidth. We are mostly focusing on low batch size inference already in our evaluation and when we build the system at the first place. So if we zoom, what got us really interested is that if we look at the performance and efficiency, it's already pretty compelling. But if we look at the utilization, what we observe is that our utilization is still pretty low in our system. So that got us wondering, like, what are the reasons for the relative low utilization that we're observing? So with that, we did a lot more characterization with our system to have a better understanding. So first, we characterize how different types of layers perform in our system. That's what we mean by layer sensitivity. So in this experiment, we designed this experiment so that we take each individual ResNet 50 layers, and what we do is that we're sweeping the number of active chiplets that are actually being used for this system and see how the performance actually scale for those layers. So what we noticed that when we first adding more active chiplets to the system, the performance or the latency, the performance definitely get better, meaning the latency actually smaller, right? So that means we observe improved performance. What we noticed that is for some of the layers, the performance improvement is basically plateaued, for example, for the one in the middle. And for some layers, actually, when you scale up to more chiplets, we actually observe slowdown for those layers. What it means is that, as we mentioned listed here, increasing the number of chiplets does not always translate to performance gains. And the cost of communication start to kick in when you actually need to think about how computation is mapped to a large number of tiles in your system. So with that, we start looking into where the latency goes, right? That in the NOC or in the knob, like why the communication becomes so important for those scenarios. So with that, we also designed two different experiments to understand that. The first one is when we try to understand the bandwidth sensitivity on the knob side. What we did is that for different layers, we can actually control the relative frequency between the network package and the processing element. With that, we can actually observe whether our layers are actually sensitive to the communication bandwidth that is available in our network on package system. So in this demonstration, we pick two layers, and then we sweep the knob frequency with the three different frequency settings. So we notice that for some layers, they're actually fairly, like for example, the one on the left, they're fairly insensitive to the knob frequency, right? So when you actually almost double the knob frequency, you only get like less than 10% performance improvement. But for some layers, they are actually fairly sensitive to the knob frequency, meaning that they are basically bottlenecked by the bandwidth available as a network on package system, which actually significantly limit the performance. Well, bandwidth is only part of the communication, right? Another side of the communication is latency, right? So we characterized the bandwidth effect earlier, and how about the latency effect? So to quantify that, we also designed an experiment by actually basically changing the placement or assignment of which chiplets actually run in what kind of layer, run in this layer. So in this example, we pick one layer and we always map to 4 chiplets. But what's different is that we're actually changing the physical locations of where those 4 chiplets are. So the one on the very left, so they're always like cornered as an upper left corner. But for the one on the right, we actually fully spread it out. So they are at the 4 corners of the package with like basically 5 hops away from each other. What we noticed that the latency of the overall layer, basically, we observe a 2.5x more latency for the placement where things are very far away. Well, notice that even for our first placement, they are only 5 hops away from each other, right? If you think about the large-scale system, even wafer-scale system, right? So we're talking about tens or hundreds of hops away from each other. So this latency effect will just become even more pronounced in a system like that. And what's even challenging is that for a system like this, programmers actually need to explicitly manage where things are and how things are moved. That's going to be a nightmare with all the different options there, right? So when you think about scalability, it's not really just a single system with this very nice memory hierarchy that hardware cache just take care of everything for you. Now you need to take care, programmer need to take care of everything themselves. Question? Yeah, so all the weights are actually on chip. So most of the communication here actually input activation multicast and also partial sum reduction. So there's actually not including the weights movement in this example. Yeah, that's a really good question. Like, oh, okay. So the first part of the question is whether the weights are on chip. The answer is yes, the weights are always on chip. And the second part of the question, what's the energy breakdown between network on chip and network on package? So we cannot measure that from our chip because we don't have that detailed breakdown. But we do have that based on the simulation. Again, it depends on the activity and depends on the layers. I would say in most of our measurement, NOC is actually become more dominant in terms of dynamic energy because we also try to avoid network on package communication in different scenarios. But one issue with the knob, more specific to our particular implementation, is that we don't really have a particular good idle mode. So for our GRS communication, it's actually always on, no matter whether the data is communicating or not. So there is a constant idle power or idle energy in that calculation. But again, it's for the dynamics, it's more depend on the tiling, or different tiling will lead to different dynamic energy. Yeah, so that's actually the ground reference signaling that we are using for the chip-to-chip communication, but there is no global clock between them actually. Only for the GRS, yeah, they need to be, but they're like for the processing element, they don't need to be synchronized. Yeah. Mm-hmm. Right. Right, that's also a really good question. I will get to more in later part of my presentation when I talk about design space. But for this particular instance of the design that we did, we also have a global buffer, actually. I didn't talk too much in this presentation. So global buffer is actually used to store the input activation. So we actually, because we target as low batch size inference, so we actually try to keep, minimize the weight movement as much as possible. So we prioritize reducing the weight movement by providing a relatively bigger weight buffer inside the PE. And for input activation, because you have tiling and locality, it's actually being communicated from global buffer to PE. So would you do normalization in the PE? You mean batch norm? Yeah, so batch norm is actually inside the PE. It's actually, yeah, batch norm is inside the PE. Mm-hmm. Here's the my question was about the ground reference. Mm-hmm. And so that's proprietary to NVIDIA, right? I believe so. Well, there's an ICC paper actually on that last year also, yeah. So what if you just use the regular? Like, so how much do you guys plan by using? That's a really good question. The question is, like, what are other, like, package level integration technology can also be applied there. We believe actually other technology can also be applied here. So especially from the architecture side, even some of the optimization, there's, and also characterization. Of course, different signaling technology will have different energy and also area profile. We need to factor that in. But typically you will be observe a longer latency and also higher energy cost for the communication that are farther away compared to on-chip communication. That will be, like if you think about scale, that will be a different scale, but this kind of scalability from architecture and the way we manage communication can also be applied to other signaling technology. Any questions? Other questions? Okay, well, let's move on. So we talk about the characterization, and finally, I'll just briefly talk about some of the, like I mentioned this kind of bit tiling space in thinking about data movement in a distributed system like this. So in today's presentation, I'll just mostly focusing on the communication aware data placement part. So in a system, in a large scale system like this, here I'm using a 4x4 for demonstration. Depends on where the producer and consumer are in the communication patterns, you may actually observe very different latency in your system, right? So if we think about a naive placement of where you put input activation and output activation, So here I'm showing a very naive input placement. We just put all the inputs to the top row and then put output activation in the second and third row. And then with that, you actually observe a lot of like communication going on between the first and second row for different input multicast and also output partial sum. So what we do is that instead of doing naive placement, you can be more aware of the communication cost between different triplets and doing a smarter placement as the one shown on the lower right, where you actually put input activation in the middle, and so that it's easier for multicast to all the different PEs that they need to actually receiving the data, and output at the corner because they actually will be used for partial sum reduction between the neighboring PEs. So with this optimization, what we observe is that up to 16% improvement for different ResNet layers because a lot of them are very communication bound. So in this work, we are interested in thinking about the scalability of the system. As a question earlier, GRS is one of the mechanisms that we use in building this large-scale system. We highlighted some of the characterization we did, especially its implication for non-latency communication, especially bandwidth and latency in a system like this. And we also talk a little bit on the optimization side, what we can do in terms of tiling and mapping to make it more efficient. So before we move on to the next part, where we're mostly thinking about design productivity and hardware design, any other questions on this part? Sure. Yeah, so we measured results for AlexNet and also DriveNet, which is more a self-driving network. So AlexNet and ResNet actually, well, of course, there's a large design space with different tiling, but they are actually pretty similar in terms of the scale of the network, where you need to think about not only just network on chip, but also network on package communication. The particular DriveNet that we use is actually pretty small, so many of them, or most of the layers, can actually fit into a single chiplet. So you observe less about this kind of strong scaling effect, and we're most experimenting weak scaling there. Mm-hmm. So there's also more control actually on the GRS side. You can also set GRS frequency. So we actually have two different GRS frequency modes that you can also set there to have different bandwidth and frequency. And with other technology, you may also have more control there. Yeah. And then also these guys are pretty small. So yeah. If you were to print it on one single die, do you have a reference point on how fast that reference speed would be? Right, so I should say this kind of a lot of the question is the dies are very small, and if we're less constrained by area, how this kind of communication would actually affect the design. So I would say this design is a test chip, right? And we experiment with what we can do. So a lot of the artifact, if you look at the relative GRS area compared to the entire chip area, is actually pretty significant. We're talking about 30 to 40% of die area is actually in communication. Typically, with this kind of spec, with this kind of sizing, a more reasonable design point, of course, a more systematic evaluation needs to be done, but a more reasonable design point is probably much larger, like talking about either one or multiple SM or 100 square millimeter, that kind of area. And then the communication is actually less pronounced, and then you can also cache more data locally, and then you're also less penalized by this kind of communication in the system. But again, that's also a large space that we also need to start understanding the trade-off in the space. Mm-hmm. So you might be saying, but so at the start you said to go towards a multi-chip module, mm-hmm. And then you showed a slide where spaceship was farther away and larger latency. So wouldn't you want to have less chiplets and just have few big ones? Right. So yeah. Right, so the question is that we have a multi-module system, and then in one of the experiments that we did, we actually spaced them pretty far apart. So in the system, a typical use case, you should actually always space them closer to minimize communication. The way we do that, mostly just the way we design an experiment to understand the latency implication, because we cannot build all the different systems with different sizing, right? So it's our way of experimenting with a signal system, but try to mimic different behaviors in the system? Yeah, great question. Okay, so let's move on, and we have more time later after the talk for questions. So next, I'm going to talk a little bit more on the productivity front, as we mentioned earlier, thinking about how we can make the design process easier and also simpler. That's our McNutt paper. So like I mentioned the Moore's Law as very early of the talk, but although the semiconductor Moore's Law is dying, but you do observe an interesting deep learning Moore's Law with increasing number of papers showing up and the new innovations coming out in like every day or even every hour, every minute. So from a hardware designer point of view, this is really puzzling when we think about hardware design, like what we can do to actually design hardware for all the different new ideas, new applications, and also how can we also like give the algorithm designers some feedback about our hardware, right? So when they design their application, not only thinking about performance and accuracy, but have some concept that those algorithms will be eventually running on different flavors of hardware. So this kind of challenge actually really motivates us to think about whether we can do hardware design more systematically or treat it more like a compilation process so that we can actually get like quickly design different hardware and also get early feedback for the algorithm development process. So with that, that's our McNutt work that was published also last year at Hot Chips and ICCAT. So what we do is that instead of designing each individual accelerator, we're taking a more generator-based approach to think about modular accelerator generation for deep learning networks. From the McNutt point of view, we take application specifications and all the different deep learning models, and internally by doing different template exploration, design space exploration, quickly generate different deep learning hardware that can be integrated with our product line. So with that, the overall goal of McNutt is to provide a modular deep learning inference accelerator generator, focusing on very reusable hardware template that you can easily tailored for your different applications and for different architectures. And we'll also highlight one of the data flow optimization we did on the multi-level data flow and to optimize our processing element architecture to improve the energy efficiency. And finally, we'll also mention the way we do design space exploration to really understand how the hardware parameters, compilation or mapping parameters, and also deep learning parameters affect the power, performance, and also area breakdown of our system. So a quick overview of McNutt. So instead of thinking like isolating hardware and software design, what McNutt trying to do is to really integrate the hardware and software design together. So there are three components of McNutt. The first one is what we call McNutt Designer. This one is more hardware oriented. This one is really thinking about whether there is what we can do to provide a highly parameterizable hardware template to enable the hardware designer to explore the different points of the design space. Specifically, we also leverage object-oriented high-level synthesis tools to quickly produce high-quality hardware RTLs to enable the fast hardware iteration. The second part is McNutt Mapper. So this is more related to the tiling complexity that I mentioned earlier, how a particular deep learning network or deep learning or layer is actually mapped to the hardware to understand the complexity in the tiling space. And finally is McNutt Tuner. We mentioned the importance of understanding the power, performance, and area implications of hardware design. And McNutt Tuner basically enables us to do automatic design space optimization, leveraging a Bayesian-based approach. So next, I'm going to step into each of the components and talk about what we did in each of the area. The first, McNutt Designer, what we're really interested in is instead of providing a point solution for each individual accelerators, if you think about the deep learning space, are those accelerators are fundamentally different, or there are those like commonly used optimizations or dimensions, and whether we can actually provide a hardware template to enable our designers to quickly evaluate those different alternatives. So with that, we actually provide a configurable architectural template for deep learning accelerator design. It has 3 different levels. One is system level, where you can actually assemble a random number of PEs and maybe also global buffers and also like your microcontrollers together to build a large system. And then if you zoom into each of the processing elements, if you think about today's all the different flavors accelerator design, all of them can be factored into some kind of storage for weight and input buffer, and some kind of pattern, access patterns with a configurable address generator. And then doing partial sum accumulation and also post-processing. And then the core of the computation is always done with a vector MAC or some kind of MAC unit to do the convolution very efficiently. One thing we do want to highlight is that even if you zoom into vector MAC units, there's like a lot of work in thinking about data flow, but if you fundamentally look at what are the differences between different data flow, it's all about different level of reuse at different type of input or output at different level of memory hierarchy. So instead of arguing whether a point solution is actually better than the alternatives, we basically provide a configurable system where you can arbitrarily add any like memory hierarchies into your system to actually enable another level of reuse. So for example, we call this collectors, both weight collectors and accumulation collectors for our vector MAC unit to actually exploit both weight and also output activation or partial sum reuse in our system. With that, just a big table of all the different parameters, mostly design time parameters, like number of PEs, size of memory, network topology, and all the different data flows that can exist in the system. I'll talk a little bit more later. And also different sizing exists at the PE level and also at the vector MAC level. So I mentioned about data flow. Many of you may already familiar with different data flow being discussed in the literature. Just a quick recap, like 2 of the data flow, especially in the context of deep learning accelerator, is basically focusing on which type of data is being reused at which level of memory hierarchy. 2 of the most commonly used data flow, one is weight stationary data flow. What it does, it basically use, like here I use 2 different colors, like blue means less frequently accessed, and the red means like you access more frequently. So basically you always want to access your large memory less frequently and access your small memory more frequently. That's basically the goal of data flow optimization. So if you look at weight stationary, it's basically trying to reduce the weight buffer access by providing a register for weight, so I can store the weights there and without accessing your weight buffer too frequently. But the downside of that is that you need to access your accumulation buffer very frequently because every partial sum needs to go to different parts of your accumulation buffer. And then, so a good example of the weight stationary data flow is like, for example, Google's TPU and also NVIDIA's NVDLA. Both of those are basically a weight stationary data flow. Output stationary data flow, instead of focusing on the weight access, we're actually more focusing on the accumulator access, basically the partial sum access. It is really important, especially when you think of precision, because partial sum always has like, it has like a higher number of bits because to keep the computation running correctly. So with that, when you optimize for output or partial sum access, typically what we do is basically adding another register to store the partial sum temporarily in the register. And then you don't need to go to accumulation buffer too frequently. But then the downside is that you always need to fetch a new weight from your weight buffer. So with that, what we are really interested, if you look at those designs, basically where you're adding the registers, right? And then why we are so fixated on only add the register as a weight buffer or only add the register as an accumulation buffer? Why we couldn't actually add the register in both? So that's what we mean actually by having a more flexible template so that you can actually add weight configurable number, configurable sizing of your registers at both weight in front of your weight buffer and in front of your accumulation buffer. With that, if you zoom in, of course, you can also have more finer grained categorization. You can still like trading off whether you're actually doing like in your innermost loop, whether you're doing weight stationary or accumulation or partial sum or output stationary. So when you add the collector there are still two different data flows. One is what we call output stationary, but local wait stationary. What it means that it means locally or the innermost, we're still keeping the wait stationary in our wait connector so that we don't need to go to the wait buffer too frequently. While on the other hand, we're basically trying to optimize for our accumulation, but instead of accumulation buffer, but it's become an accumulation collector. So it's a much smaller register file. And then the more frequent access wait access go into wait collector, which is still much cheaper because it's a smaller register file instead of a larger SRAM. And in reality, we typically implement those wait collector and accumulation collector can be just implemented as latch array instead of SRAM, which is also more energy efficient. So with that, you basically have a template that the user can actually configure and easily try out all the different data flow on their own for their design. Later, I will show some more quantitative evaluations of how that actually affects the design space of deep learning accelerators. So next, I'm going to very briefly talk about the mapping. I think I already mentioned that in the earlier Simba design, basically how you actually map a convolution onto your processing element, both temporally or spatially. There are different mapping strategies, and a more systematic way of thinking about that is also in our time loop paper that was published at ISPAS last year. That was all more a higher level way of thinking about both performance, energy performance modeling, and also evaluating the mapping space. So those are the different runtime parameters, focusing on temporal and spatial mapping, and we also support fusion as a mapping option that can be configured during the runtime. So just a quick example in terms of the size of the mapping space. So we care about why mapping actually matters. So this actually resonates with the result that we see earlier also really well. So this is basically the same type of hardware, and each of the group we're showing here is basically the same layer. So your application layer is fixed, your hardware is also fixed. The only thing that is changing is actually how you map the computation to your hardware. So that's what we mean by the map space here. So here we evaluate both performance and energy for two different layers and just see how the different mapping actually translate to more than 10x performance and energy efficiency difference. So that's why we really need to think about not only just the hardware design, but also how the application will be mapped to the hardware and whether we have a really reliable solution to help the programmers to understand the complexity of the space. And question? Mm-hmm. Yeah. Symmetric? You mean this group here? Uh-huh. Well, I guess this one is less symmetric, right? Yeah. I would say it's like well, I guess depends on where you look at. I wasn't say, either you look at the energy for this one, right? It's also less, or you're talking about like, that's just the way the plot works, actually. So the x-axis doesn't actually mean anything. It's called a swarm plot. It looks really cool, and we plot it that way. But the x-axis doesn't mean anything. So it's basically just all the x-axis are the same because they are basically the same application, the same benchmark, right? So this is just a way to show all the points, but in a flattened way so that you see all the points. Yeah, so it's just an artifact of plotting, yeah. But I was originally thinking whether you mean like vertically they are symmetric. Yeah, it's different. I would say it's like they typically cluster in the middle because they're like more tiling options go to like similar performance, but it's really challenging to find the best one, basically. It's very easy to stuck with a mediocre one, but it's more challenging to find the best one. Yeah, that's definitely the case. Okay. All right, so like another challenge, actually, more like a challenge we run into is that when you actually tie all the different things together, right? We talk about flexible mapping, flexible template in hardware, flexible mapping in our application, in our software, and also with all the different tools placing together, each of the run become a lot more expensive than we expect, and then it's become an optimization problem. Is actually how do you efficiently navigate the entire space to find a good hardware design point, but also a good mapping point. So I wouldn't get too much detail in this part of the talk, but basically to help us stay sane in terms of evaluating the entire design space, we basically adopt a Bayesian optimization-based approach by randomly sampling a small subset of the data, and by continuing adding new samples, we build a probabilistic model of the design space, and to help us to quickly find the performance and the energy optimal designs instead of doing an exhaustive search, which becomes basically infeasible for a complex system like this. Okay, so come to the evaluation section. Like we talk about we use different benchmarks and also different tools in the system, and we put together all the different design spaces for our designers and also mappers here in our design space evaluation. So first I'll talk about the entire design space when we factor in all the different runtime or design time parameters in the system for different neural network. So the one on the left is our result for ResNet 50. So if you remember earlier what we see with the Simba system that we started is roughly 0.1 picojoules per op. That is basically the spec that we get. And then by doing a more systematic design space evaluation with McNutt, sweeping all the different, for example, precision for both input activation and also weight, all the different design time parameters that we listed here with different data flow, different size of the memory, and also different mapping here. So here we highlighted some of the results that we have here. So if you look at the best performance per op one, I believe it's 40 ops. Yeah, 40 femtojoules per op, which is also significantly better than the ones that we got from our Simba test strip by exposing this large design space to the designers and evaluate this very systematically. And this is also using the 16 nanometer technology from TSMC, yeah. What do you mean fast? You mean the Bayesian optimization part? No, it's not days. So basically, if you look at this, right? So we're talking about roughly 20 to 40 runs, then you will be able to roughly find a reasonably good ones, right? And the one thing really nice with our system, I didn't talk too much on the high-level synthesis part, but the performance is actually a lot easier than energy, like power estimation is the slowest one. That takes the longest time. But we can actually get performance feedback reasonably well by using a System C-based high-level synthesis flow. So we're basically just running high-level synthesis System C simulation, which is purely basically a C++ simulation in the design process, instead of doing Verilog simulation. And they are basically just the speed of, for the large-scale system, they also slow down, but they are pretty reasonable. We're talking about like 10 kips as a fast simulator. So I think that also simplifies the design process reasonably well, at least to find a reasonable performance efficient one. Mm-hmm. Yeah, so that's a really good question. Let's see, do I have that? Yeah, so those three are basically for different networks, right? So for the McNutt, there are different ways you can use that, right? So you can treat it as different network. That's what we did in the system. So we have ResNet, LXNet, and DriveNet. So everyone is individually, right? But then you can also do that. Like, how about I actually want to find someone for 2 or 3 network or all the different networks, right? So then you have a lot more front-end parameters with different applications, but then you need to consolidate those parameters, those like different design sweep space together, right? So the approach that we took is that we enable designers to try out different things. It's possible that you want to design a more like tailored to ResNet style network hardware, then it will be more like this, the one on the left. But if you actually care all the different applications, then you need to really think about all the different inputs. Mm-hmm. Yeah, so this is pretty compelling based on what we have been observing in our community, basically. Any other questions, comments? That's a good question. So this study actually not including the NUP. So the NUP is really just for the prior. That's a more specific multi-chip module basis. Oh, the question is whether we still consider NUP in this evaluation. So the NUP is not part of this. Yeah. Okay, so another result we'd like to highlight here is that we talk about the effect, like the reason about data flow and the possibility to support a multi-level data flow based approach. So, so if you think about some